Most astrobiologists are not looking at Mars. Mars gets the missions, the rovers, the headlines, the photographs of rust-colored dust storms. Mars is the story the public knows because Mars is where the hardware is. But in the rooms where researchers actually argue, in the seminars, the proposal reviews, the late sessions at planetary science conferences, the conversation keeps returning to a moon the size of our own, 600 million kilometers further out, locked in orbit around Jupiter, covered in a shell of cracked ice. Europa. The surface temperature sits around -160 degrees Celsius. The atmosphere is essentially absent, a trace of oxygen, too thin to detect without instruments, produced not by biology, but by radiation splitting water molecules on the ice. Jupiter's magnetic field hammers that surface with radiation intense enough to kill an unprotected human in less than a day. Nothing about the surface of Europa is hospitable. Nothing about it invites a second look. And yet the second look is where the entire conversation lives. The reason Europa is the serious conversation, not the speculative conversation, the actual peer-reviewed funded mission conversation, is not about anything on the surface. It is about what is 60 to 150 kilometers underneath it. There is a liquid water ocean beneath Europa's ice. This is not a hypothesis being tested. It is a confirmed result, supported by multiple independent instruments across 3 decades of observation. The ocean is global. It wraps the entire moon. It has been liquid for a very long time, possibly for the entire span of Europa's existence, and it is deep. Our best current estimates put it at 60 to 150 kilometers of liquid water. The Challenger Deep, the deepest point in Earth's oceans, is not quite 11 kilometers. Europa's ocean, by volume, contains more liquid water than every ocean on Earth combined. That is not a poetic comparison. It is a constraint on probability. In the summer of 1979, 2 spacecraft swept through the Jovian system on their way to the outer solar system. Voyager 1 had passed in March. Voyager 2 arrived in July. Their primary targets were Jupiter and the large moons, Io, Ganymede, Callisto. Europa was on the schedule, but it was not the focus. It was one stop among several, expected to be interesting and not expected to be the most interesting. Bradford Smith led the imaging team. He was a planetary scientist at the University of Arizona, and by the time Voyager 2 reached Europa, his team had already been through something that had changed the mission entirely. Io, the volcanic moon. Sulfur plains and active eruptions, something no one had predicted. Smith and his colleagues were still processing what Io meant when the Europa images came back. Smith sat at the console and looked at a surface unlike anything in the solar system. Not the cratered terrain everyone expected from a moon that old. Not the broken geology of Ganymede. Something smooth. Almost completely smooth. A few craters, far fewer than any comparable body. And that absence is itself a signal, because craters accumulate over time, and a surface with almost none is a surface that has been recently refreshed. And crossing that smooth terrain in every direction, lines. Dark brown lines, some thousands of kilometers long, some narrow, some wide, crisscrossing the globe in a pattern that looked to several people in that room like the surface of a cracked egg. Smith later said the surface looked like it was trying to tell them something. The lines were not random. They had structure. They implied movement. What had moved the ice was not a question the data from a flyby could answer. The resolution was not sufficient, the coverage was not complete, and Voyager 2 had a solar system to cross. Smith filed the observation. The team moved on. That image, those lines, that cracked, smooth surface, sat in the archive for years before anyone had the instruments to ask it the right question. Here is what Bradford Smith was looking at and could not yet explain. Europa's ice shell is not static. It bends. Jupiter's gravity and the gravitational pull of the other large moons, particularly Io and Ganymede, which tug on Europa as they orbit, creates tidal forces that squeeze and stretch the moon on a cycle locked to its orbital period of roughly 3.5 Earth days. That flexing generates friction. Friction generates heat. That heat, sustained over billions of years, keeps a layer of water liquid beneath the ice. The dark lines are fractures. The ice cracks under tidal stress. Material from below wells up into the cracks, refreezes, and leaves a dark residue. Some of those lines are spreading bands, places where the ice has actually pulled apart and new ice formed in the gap, the way the seafloor spreads along mid-ocean ridges on Earth. Others are ridges where two ice plates compressed and buckled upward. The surface is not frozen in place. It is in slow, continuous motion, driven by an engine that has been running since the solar system was young. The oldest ice on Europa is probably no more than 90 million years old. The moon itself is 4.5 billion years old. The surface turns over. It refreshes. Material from the ocean below is cycling toward the surface. Material from the surface, compounds built by radiation chemistry, may be cycling back down. This is not a sealed system with a frozen lid. It is a system in motion with a boundary that moves. Margaret Kivelson was at the University of California, Los Angeles, working through magnetometer data from the Galileo spacecraft's Europa flybys in 1998. Galileo had arrived at Jupiter in December 1995. It was not the first spacecraft at Jupiter. Voyager had been there, Pioneer had been there, but it was the first to orbit, the first to stay, the first to make repeated close passes of the large moons. Europa got 11 close flybys over 8 years. Kivelson's magnetometer was running on each pass. She was looking at the magnetic field data, and she found something that should not have been there. Europa was generating a magnetic signal, not an internal field of its own, because Europa does not have one, but an induced field, a response. Jupiter's magnetic field rotates with the planet, sweeping past Europa on a regular cycle, and Europa was responding to it. The physics of induced fields is not complicated. If you have a conductor inside an oscillating external field, the conductor generates a response field. The character of the response tells you about the conductor, specifically about how well it conducts electricity. Ice is a poor conductor. Rock is a mediocre conductor. Salt water is a good conductor. Kivelson sat with the data for months. The induced signal was present in every flyby. It was consistent. It was at exactly the strength and phase you would predict if there was a globally continuous layer of electrically conducting fluid beneath the ice, a fluid that wrapped the entire moon. The signal was not consistent with a localized pocket. It was consistent with a global ocean. She published in 2000. She was careful. The data was consistent with a subsurface ocean of salty water. She was not claiming more than that. The implication was clear to everyone in the field: a global liquid water ocean in contact with a rocky seafloor, because the ice floats and below the ocean is rock, not ice all the way down, rock at the bottom. The most consequential thing Kivelson's team did in 2000 was not confirm an ocean. It was convert the search for life from a question about the cosmos into a question about our neighborhood. On Earth, life did not wait for sunlight. In February of 1977, a small submersible named Alvin descended into the Pacific Ocean along the Galapagos Rift, a section of seafloor where tectonic plates pull apart. The geologist Robert Ballard was part of the dive team, and they were looking for hydrothermal vents, superheated water saturated with dissolved minerals, venting from cracks in the seafloor where seawater meets magma below. They found the vents. They found something else. Around those vents, in complete darkness more than 2.5 kilometers below the surface, where no sunlight had ever reached and no photosynthesis was possible, there was life. Not scattered microbes. An ecosystem. Tube worms more than 2 meters long, with red plumes visible from the submersible's lights, clams, crabs, shrimp. A food web with no connection to the sun, organized entirely around bacteria that draw energy from the chemical reaction between hot vent fluid and cold seawater. Ballard described surfacing and not being able to make the other scientists believe what he was saying until they looked at the photographs. Since 1977, hydrothermal vent communities have been found in every ocean on Earth, at every depth where vents occur. The biosphere extends into permanent darkness and crushing pressure and near-freezing water and temperatures above 300 degrees Celsius at the vent exits, conditions that would kill most surface life immediately. Every time we extend the boundary of where life exists on Earth, we extend the set of places in the solar system where it might exist. Europa's ocean floor is almost certainly in contact with hydrothermal activity. The same tidal flexing that keeps the ocean liquid also drives geological activity at the seafloor. The energy budget is large enough that hydrothermal circulation is expected. Whether communities similar to those on Earth exist there, we do not know. But the physical configuration, heat, liquid water, rock, chemical gradients between hot vent fluid and cold ocean, is present. That is the configuration that produced the tube worms. "4 billion years is a number I cannot hold in the same way I can hold other numbers in this field, and I am not sure that failure is a limitation of imagination rather than a correct response to what the number actually means. 4 billion years is how long Europa's ocean has probably been liquid. It is also approximately when the first chemical signatures of life appear in the rock record on Earth. Not confirmed organisms, chemical traces, carbon isotope ratios in ancient zircon crystals from Western Australia that are consistent with biological processing of carbon, dated to around 4 billion years ago. The first confirmed microfossils, structures that closely resemble modern photosynthetic bacteria, appear in rock formations dated to 3.5 billion years ago. Life on Earth appears to have arisen very quickly after conditions stabilized. Within a few hundred million years of the end of the heavy bombardment period, within a short interval after liquid water became available on the surface, something began metabolizing. We have one example of this process. You cannot build a probability distribution from one example. But the single example we have shows life arising at the earliest plausible moment, and that is at minimum consistent with the idea that life is not a singular accident, that it arises when conditions allow. Europa has had conditions that allow for 4 billion years. And there is something else, something found not in a laboratory but in an archive. In 2012, Lawrence Roth was at the Southwest Research Institute in San Antonio, working through ultraviolet images of Europa taken by the Hubble Space Telescope. He was examining the limb of the moon, the edge of the disk, and he found a transient feature near the South Pole. A burst of water vapor extending roughly 200 kilometers above the surface. It appeared in one observation. It was gone in the next. Roth published in 2013. The result was immediately contested. A single detection, instrument limitations, alternative explanations still possible. Then, William Sparks at the Space Telescope Science Institute in Baltimore found similar features in 2016 in a different dataset using a different instrument in absorption against Jupiter's disk. Transient plumes, South Pole region, different technique, same result. Then, a team led by Xianzhe Jia at the University of Michigan went back through Galileo's archived data in 2018. They found that during one Europa flyby in 1997, Galileo had passed directly through what appears to have been a plume. The magnetometer readings from that pass, readings filed away for 20 years, showed signatures consistent with a dense column of ionized water vapor erupting from the surface. Galileo flew through a Europa plume in 1997. Nobody knew until 2018. 3 independent lines of evidence, 3 different instruments, 3 different teams, all pointing at the same thing, material from Europa's interior venting directly into space. A spacecraft flying through one of those plumes could sample the chemistry of the ocean without drilling, without landing, without touching the surface at all. The Europa Clipper spacecraft launched in October 2024. It is the largest planetary science spacecraft the space agency has ever flown, not because the mission required something enormous for its own sake, but because it is carrying 9 scientific instruments and enough shielding to survive repeated close passes through the radiation belt surrounding Jupiter. Robert Pappalardo is the project scientist. He has been working on Europa since the 1990s when he was a graduate student and Galileo's data was coming back. He has spent most of his professional life building the case for this mission, writing the science, making the arguments to funding bodies, helping design the instruments. When Clipper launched from the Kennedy Space Center in Florida, he was standing on the causeway watching the rocket climb. He said afterward that it felt less like a launch and more like the beginning of a sentence. He had spent 30 years writing the setup. The sentence was now in motion. Clipper will not orbit Europa. The radiation environment would destroy its electronics within months. Instead, it will make nearly 50 close flybys of the Moon over the course of its primary mission, each one targeting a different region, building a global picture from repeated passes. Each flyby lasts minutes at closest approach. The rest of the orbit carries the spacecraft far enough from Jupiter to let the instruments recover. The science payload maps the ice shell, measures the ocean's magnetic signature, analyzes the thin atmosphere, looks for heat anomalies on the surface, and, if the spacecraft passes through a plume at the right moment, samples the material venting from below. The radar instrument is the one that carries the most structural weight for what comes next. It is designed to measure the thickness of the ice shell directly, not inferred from models, not estimated from surface features, but measured. The answer matters for a reason that goes beyond science. Any future mission to access the ocean depends on knowing what stands between the surface and the water. The obstacle is the ice, and the uncertainty about the ice is large. Current estimates for the thickness of Europa's ice shell range from 3 kilometers to 30. 3 kilometers and 30 kilometers are not similar numbers. A 3-kilometer ice shell is penetrable with technology we could build on a timeline we could fund. A 30-kilometer ice shell is not in any mission that exists on paper, not in any budget window that anyone is currently discussing. The range is not a failure of the models. It reflects a genuine ambiguity in the data. The surface features, the lineae, the chaos terrain, the lenticulae that look like frozen lakes, are consistent with a range of ice thicknesses. Kivelson's magnetic measurements constrained the ocean, but not the depth of the ice above it. Galileo's flybys were not designed to measure ice thickness. Clipper's radar is designed specifically for this. It will map the structure of the ice shell across the globe, looking for the transition from solid ice to liquid water, looking for pockets of melt within the ice where surface chemistry and ocean chemistry might already be mixing. We will have a much better answer after Clipper's primary mission. What we will not have after Clipper is a sample. We will not have an image of the ocean floor. We will not have any direct evidence of life or its absence. Those questions belong to a mission we have not yet designed, funded, or built. And that mission, whatever it turns out to be, will need Clipper's data before it can know what it is trying to do. Bradford Smith looked at cracked ice in 1979 and could not explain what had moved it. 45 years later, a spacecraft the size of a school bus carrying 9 instruments specifically designed to answer that question entered the Jovian system. The gap between those two moments is not empty. It is filled with Galileo's magnetic measurements, with Kivelson's data, with the plume observations, with 3 decades of theoretical work on tidal heating and ice shell dynamics and hydrothermal chemistry. Every piece of work in that gap was trying to close the distance between what Smith saw and what it meant. What Clipper is doing now is what Bradford Smith could not do in 1979, asking the ice a direct question. The question is not whether there is life. Clipper's instruments are not designed for biosignature detection. The mission is ocean characterization. How thick is the ice? How salty is the water? Are the plumes real and consistent and accessible? Are there pockets of liquid within the ice shell where chemistry from above and below might meet? What Clipper will produce is a target, a constrained, specific, scientifically defensible target for the mission that follows it. The mission that follows it is the one that might answer the question Bradford Smith could not ask. Here is where the knowledge stops, exactly. The ocean is confirmed. It is global, liquid, and in contact with a rocky seafloor. The tidal heating mechanism that keeps it liquid is well understood. The surface is geologically young. The ice turns over on a timescale of tens of millions of years. Plumes are almost certainly real. The volume of the ocean exceeds the total volume of Earth's surface oceans. The physical configuration, heat, water, rock, chemical gradients, matches the configuration that produces hydrothermal ecosystems on Earth. What we do not know, the thickness of the ice shell with enough precision to plan a drilling mission, the salinity and chemistry of the ocean, whether hydrothermal activity at the seafloor is active now and at what scale, whether the oxidants produced by radiation chemistry on the surface are reaching the ocean in quantities large enough to support a metabolic food web, whether the plumes originate from the ocean itself or from liquid pockets within the ice. Kevin Hand has spent most of his career at the Jet Propulsion Laboratory working on this problem. He describes the habitability case for Europa this way: the physical and chemical conditions required for life as we understand it are present. Habitable does not mean inhabited. Habitable means the conditions do not prevent life. Whether anything has ever used those conditions is a separate question, and it is the question that no instrument currently in space is positioned to answer. The boundary is not vague, it is precise. We can draw the line between what we know and what we do not with more accuracy for Europa than for almost anywhere else in the outer solar system. What is on the other side of that line is the question. The ocean is there. It has been there for billions of years, and we have never once been able to say that about anywhere other than here.